now, wouldn't it? And the derivative would be 0, right? That would have no impact on this, would it? If I move the whole circle up 2, this would be 2, and then derivative would be 0, and it would have no impact on this. Do you see that? Nowhere in this formula is the original function, just the derivative. So it doesn't really matter where we place that circle in three-dimensional space, as long as it's a circle in the xy plane, so to speak. All right, I need the second derivative. All right, second derivative, negative cosine t, negative sine t, 0 again. Pretty clean derivatives. I need magnitudes of things also, right? But do you all see I need a cross product of these two? Let me do that over here. If I do the magnitude, I'm sorry, not the magnitude, the first derivative crossed with the second, then that's going to be a vector, right? It's going to be a vector. It's going to have 3 pieces to it. And I have to do a cross product on these two, right? So remember how we do cross products, right? We write the 2 vectors down, which I'm just going to leave them here. I cover up the first piece, and I do the determinant here. What do you get with that determinant? 0, right? You'll see that? 0 minus 0, 0. Okay, so we get 0 for the first piece, comma. All right, now I cover up the middle one. And remember, I'm going to multiply by -1 here. Okay, but what do I get when I do that determinant? 0 again, right? You get 0 here, 0 there. So we got a second 0, so I don't need the -1 there. And then finally, we cover up the last piece, and whoa, what do we get there? So here to here gives you sine squared, right? And then minus negative cosine squared t. So this really becomes sine squared t, I'll do it, minus negative cosine squared t, but that's the same as sine squared t plus cosine squared t, so this is really 1, right? It's 1. So we get the vector 0, 0, 1. Okay, that's the top. That's this piece right here. Now we need the magnitude still. So I'm moving along. Let's find the magnitude of that. The magnitude of this cross product should be the magnitude of this vector, which is the square root of 0 squared plus 0 squared. I don't think I needed to do this, but I think it's obvious, right, that the magnitude of that vector is 1. But that's the work for it, right? This is 1. So I've got the top, right? In terms of what I've done here, I've got all of that done now, right? I just need the magnitude of the first derivative cubed. So the only thing left. So I never did the magnitude of the first derivative, did I? No. So I need it right here. I'm going to do it right here. What's the magnitude of that? Well, it's the square root of, and we've done this already, haven't we? Okay, but I'll do it again. It's going to be negative sine t, that squared, plus the cosine t, that thing squared, plus 0 squared. And that gives you 1. Because again, Pythagorean identity. So you get 1 over 1. So our curvature, is constant. Curvature is constant. Yeah? Yes?
For it to be constant, we just need that to come out to a constant.
Yeah, it needs to be a number, right? Instead of something that has a variable appear in it, like the next example. Yes?
So I did it sort of differently.
Okay.
I found the magnitude for both r prime and r double prime. I found them both to be 1. So the cross product is just an area. So 1 times 1 is 1. And it just came
It's the area.
It's because I used the magnitude version of it, where it's like magnitude of u times magnitude of v.
Times
Sine theta. Right?
So do you know what theta is, though?
I guess I'd have to count it there without.
Yeah, you would need that. So you would need to, the only thing you would need there is to, if you could show that r prime and r double prime are orthogonal, then you could use that. Yeah. which, yeah, I don't know. Is that always the case? Is R prime always orthogonal to R double prime? I'll leave that as an open question. I think in certain circumstances, yes. In others, maybe not. All right, we're good? Two-dimensional vector. We found the curvature, vector function. We found the curvature by extending it into three-dimensional space. And I haven't figured out what this error is yet. I was trying to figure it out this morning. I'll figure it. Here's a different curve, okay? Just by looking at it, this does not look like it has constant curvature, right? If we started drawing this in the beginning, right, it's really tight curve, right? Really tight turns. And then as you go out, that turn kind of widens out so you wouldn't be curving as much, right? So the curvature for this vector function should be a function of where we are on the curve. It should not be constant. Let's see if we can show that. And so I need to give you what the vector function is, and I actually don't know if I am going to give you that vector function. Yes?
We have a unit of measurement for curvature.
As far as I know, no. It's just a numerical value.
Okay.
Yeah, I mean, you could put some. I mean, think about if it was really like in space. If you knew what, feet, inches, you could do like a change, rise over run. You could do something like that.
Okay.
But the problem with that is, if I'm at this point and let's say I'm moving along this curve and I'm trying to figure out the rate at which I'm turning, the measurement in this direction, if they're the same units, then the ratio is going to be 1, like feet over feet, feet per foot, right? So I'll double check on that, but I do not believe that there is a quantity for it.
Okay.
I thought we were going to do this one. Hold on. Because this one right here is really simple. I thought we were going to do this. Let me open this up real quick. Come here, open. I'm afraid to try this one because I'm afraid we might get ourselves into a big mess. All right, it's not in the notes. I'm not going to do it. Maybe come back. Let's do this one because this one is not, the curvature here is not constant, but it's not a tough vector function. So here we go, find the curvature. So I'm going to need the first derivative, right? So first derivative of this, pretty straightforward. Do derivative of each one of the components, like that, right? That's our first derivative. Second derivative is what, 0, 0, 2? Real quick, are these orthogonal? I'm getting to are these orthogonal? How do you check if these are orthogonal vectors? Dot product, is the dot product 0? This times this, plus this times this, plus this times this. The dot product of this is 4t. So that's only 0 when t is 0. Any other point, there aren't orthogonal. So if you were going to use that other formula for this, you would need to know the angle. Yeah. All right, I'm continuing. Would you all like me? I have two choices here. I can go do the cross product and get its magnitude like we did before, or I can get this magnitude now. You want to just follow the same format I just did? Same format? Okay, so I've got those two. Okay, now I need to take those two and cross them together. And that will be a new vector. Okay, let me go through this. So I'm going to get the first component, I cover these two up, and I do a determinant. 2 minus 0, right? So 2. Then a negative 1. And now I cover up the middle one, and I get 2 minus 0 again. So 2. And it'll be negative. And then the last one, 0. So this is the vector, I'll do it here. This is the vector 2, negative 2, 0. So okay with that? That is your cross product of your first and second derivatives. I need the magnitude of that now. So the magnitude of that, square root of 8. So just square each component, add them up. 2 root 2 if you want. I'm just going to leave it like that. And last thing, I need the magnitude of the first derivative, right? So the magnitude of the first derivative is going to be the square root of, okay, my first derivative is right there, right? So I'm going to do 1 squared plus 1 squared plus 2t squared. So 1 squared plus 1 squared plus the quantity 2t, square that. You should get root 2 plus 4t squared, right? 1 plus 1, that's 2, and then that squared is 4t squared. And now I'm going to just take my formula, right? Curvature is equal to the magnitude of the cross product, which we found to be the square root of 8, over the square root of 2 plus 4t squared. You could leave it like that. You could put it all into one root if you want, because that's a property of radicals, right? Question? Oh, I forgot to cube it. Thank you. Oops, that's not right then. I way ahead of myself there. Is that what you were going to say? Yes? Okay. I'm glad y'all are paying attention. It's definitely the Monday after Super Bowl for me. 2, 4t squared, and then cubed. Yeah, so I'll just leave it like that. I'll just leave it. I could somehow put those together. I don't want to. Okay, so there's something really interesting. Was there a question?
Does that little formula find the curvature for any point at t now?
At any value of t, this gives us the curvature, right? So if I go back to that picture, well, I don't have the picture here. This is not that. But what I could tell you is this, that as t gets bigger, the curvature gets smaller, right? Because if t gets bigger, the denominator gets bigger. If the denominator gets bigger, this ratio gets smaller. So the bigger the t is, the smaller the curvature is. So I can imagine that in this curve, the further out, whatever's going on, because I didn't graph this. We can go graph it if you want.
We should graph it.
We can graph it. What I know is that the further out t gets, right, time, if we look at it as time, I know that I have a smaller curvature. Let's see if we can graph it. And I'm going to try and use this 3D calculator. I forgot how to do it. Parenthesis, was it t, comma, what was the vector function?
1 plus t squared.
1 plus t squared? Yeah, okay, this makes perfect sense. The vector function, so we're looking at the vector function. We're looking at the vector function r of t equals t, what was it?
1 plus t squared.
1 plus t squared? Okay, so in the xy plane, right, in the xy plane, that's the same as y equals x. So in the xy plane, it's just trying to draw a line, the diagonal, the identity. But in the z, it's trying to draw a parabola that's been shifted up 1. So it's like you're drawing the parabola along that line. And so that's why it looks like this. Right? And do you agree that as t goes on, right, if you're moving along this curve, if t is like close to 0, you're down here somewhere, and you've got a really tight curve there. But the further you go, it's just a slower and slower turning. Yeah? Okay, we can see that from the curvature formula that that's going to happen. Yes?
So the limit of this as it approaches infinity, the curvature would approach
0. It's exactly, yeah, so that's what I'm saying. If you go out on that parabola like to infinity, you're essentially like straight line.
I was about to ask, well, would it ever actually get to no curve? And then I realized, oh, wait, no, at the limit of t.
It would be the limit, yeah. All right, so that's curvature. We good? We're moving on. Chapter 10. Oh, wait, there's one more thing in curvature that I don't have in my notes. that I am going to take from the book. I normally don't put this in here, but I'm going to. There's one more thing that I want to define for us. This is called the unit normal vector. So this is an additional, this is in the textbook, but it's just not in my notes. So all this is capital N, it's this vector capital N of t, and it is defined to be the derivative of the unit tangent vector over its own length. So the derivative of the unit tangent vector divided by its own length. This is, oh, well, page doesn't help you. You have an ebook, right? Yeah, so as a reminder, let's say I have a curve here, okay, sitting in space. Let's say that this is r of t, right? Then if I go to some point on this curve, let's say here, then I'm going to get a tangent vector. That's r prime of t, right? That's r prime of t. Then, if I take this vector that's tangent to the curve at that point, and I normalize it, I make it have a unit length, a length of 1, I get capital T of t, right? That's our unit tangent vector. That's that vector divided by its own length, right? We did that last class. This vector is orthogonal to that red vector. But it's also orthogonal to another thing called the binormal vector. I'm not going to get too much into it, all right, because I don't want to drag us off topic. We'll need this vector later, though. So this can be in different directions. I'm going to just draw it like this. That's our n of t, all right, orthogonal. What makes this a little bit tricky is, imagine that this stick right here is the t, right, the capital T. That capital N vector can be a bunch of different vectors, can't it? Think about all these vectors that are orthogonal to this. But it's one specific one. I don't want to get too much into which one it is. We'll readdress this later. I just want you to know like what the computation is. If you're ever trying to find the unit normal vector, then all you have to do is find what capital T is, take its derivative, and then scale it by its own length. And then you will have the unit normal vector. Right? I think in your homework it does ask for you to find the unit normal vector. So, okay, that said, let's move on. Chapter 10 is history. We now move to chapter 11. Now, chapter 11 in the book, do I have the title of the chapter here? Let me see. That's 11. No. So chapter 11 is called partial derivatives. That's the name of the entire chapter, partial derivatives. And we are starting with 11.1, which is titled Functions of Several Variables. This section, there's not a lot of computation to do, all right, not a lot of derivatives and things. It's really just us understanding what's happening. So we have already seen, this is something I've talked to you about before, in the past, when we have functions like this, anything that we've studied, right, function like that, what's happening here is we're taking in this function, takes a real number in, and spits out a real number. So we could say that this goes from one-dimensional space to one-dimensional space. Now what we're doing is we're going to do something a little different, all right? We have already seen up to this point that when we have equations with x, y, and z in them, we have surfaces. That was last class, right, when I was sitting there like, this is a paraboloid, this is an ellipsoid, this is a hyperboloid of two sheets, all that stuff, you know? We're just showing the pictures. And okay, we already know that we see x, y, and z together, we should expect to see a surface. Now, if we have that equation that has x, y, and z in it, whatever the equation is, if we can somehow isolate the z in the equation, if we can get it by itself, then we can say that that z is a function of the other two variables. That's kind of like this when we have, if I were to give you, let's say, x minus y equals negative x. If I gave you that equation, that has x and y in it, right? Can you get y by itself? Sure, I can move the x to the left and then the y to the right. Now I've isolated y. And now what I can do is I can say, oh, let me say y is a function of x. And then I'd write that down, right? Same exact principle. If we have all three variables together, x, y, and z, if we can get the z by itself, then z can be looked at as a function of the other two variables. Now, whenever we deal with functions, we still have this property that when you have one input, you can only have one output. Right? That was the property of a function. If I plug in a value of x, I can only get one value of y out. Same principle here. If I plug in one value of x and one value of y, I should only get one value of z to come out. With this notation, it is important to see that the domain of the function, if I'm going to use this, if I'm going to use this notation, that z is equal to some function of x and y, it's important to see that the domain of this function are all the ordered pairs, x and y, that can be plugged into the function without there ever being a problem. I'm going to give you an example, all right? But the domain lives in two-dimensional space as opposed to one-dimensional space. And then the output is in one-dimensional space. So this right here, this function, goes from two-dimensional space into one-dimensional space. I feed it an x and a y, and it spits out a z, which is a value. So you go from your input coming from a plane, x, y, a point on a plane, and that somehow gets mapped to a number line, some number here. So to visualize this, I'm going to need 3 dimensions to visualize it. 2 dimensions for the input, 1 dimension for the output, which means 3-dimensional space, right? So I'm going to show you pictures. We're going to get into what these all look like, but I want to just start off algebraically, just to make sure we understand how this works. So I've given you your first function up here, f of xy equals the square root of x plus y plus 1 all over x minus 3. And the first thing I want to do is find f of 2, 1. That just means you're going to take that function, replace x with 2 and y with 1. That's it, right? So for part A, f of 2, 1 means square root of 2 plus 1 over 2 minus 3. So that's square root of 4 over negative 1, which is negative 2. Agree with me or no? RG. I just realized this is not following the right-hand rule. No, that's the way I had it. All right, so let's see if you can make sense out of this. Right-hand rule, right? Right-hand rule. RGB, red, green, blue, right? So x-axis, y-axis, z-axis. If x is 2, 1, 2 on the x-axis, and y is 1, come out 1 unit here, right there, my z value will be negative 2, which means down 2. That's 1 point, right? Yes? Okay. Let's now go to the next one, f of 0, 0. If I do that, I get square root of 0 plus 1 over 0 minus 3. This is 1 over negative 3. So negative 1/3. So in my kind of picture here, at the origin, right, at 0, 0, x and y, I need to go down 1/3, and that'll be the point. And then how about C? For C, f of negative 4, 1, we get square root of negative 4 plus 1 over 4 minus 3. Okay, hold on. Hold on. Was it negative 4? Wasn't it?
Yeah.
Negative 4 plus 1, yeah.
Negative 4 minus 3.
Oh, on the bottom. Yes, yes. Is that what that's what you're saying?
Yeah.
Yes. Okay. What's wrong here? We have a negative underneath that root, right? We have a negative under the root, which means what? You can't imaginary, right? We can't do it, right? I told you a while back, Cal 1, Cal 2, Cal 3, we don't deal with imaginary numbers at all. So we are stuck. So what we say here is that this point, right? This is not in the domain. This is undefined, right? We don't have a way of defining this. So this right here, this point, is not in the domain, right? That point is not in the domain. If I go and I try and go to negative 4 on my x-axis, 1, 2, 3, 4, and I go to 1 on my y-axis and I try and find a point, I don't have one. I don't have one. All right, now let's determine the domain. If there are some points that work, right, some points can get plugged in and some points cannot get plugged in, then I want you to tell me what points can and what points can't. They live on a sheet of paper, right? It's basically like the ground here. Tell me all the points on the ground that can be plugged in. So the way I'm going to do part C, or part D, is this. For part D, I'm going to analyze the function and I'm going to see where I have problems. So the first thing that's kind of glaring at me is the fact that I can't ever let x be 3. Because if x is 3, we have division by 0, right? So that's the first thing. When I'm talking about domain of this, I know that x cannot be 3, for sure, right? The other thing, right? I just want to make sure it didn't get moved. Okay, the other thing is that what's underneath the root, the radicand, right? That's the radicand. That's the part that's underneath the square root. That cannot be negative, right? Or else I'm in trouble. So I need this to be greater than or equal to 0, right? Greater than or equal to 0. I'm just going to make sure I did turn on my recording here. I forgot to flip this over. Yeah, I'm recording. All right. So for this, I'm supposed to determine the domain and then sketch the domain. So as far as domain, this is kind of enough for me to just say what it is. This has to be true and this has to be true, right? So if you wanted to write this in a more precise way, you could write domain of f, dom f, is the set of all ordered pairs x and y. So all the points that you can think of in space. This bar means such that. Some textbooks use a colon here, but a lot of textbooks use a bar. So this means all points such that x is not equal to 3 and, and you could do comma. X plus y plus 1 greater than or equal to 0. That's the more precise way to write what the domain of this function is. Now I want to sketch it. So let's start with this x can't be 3. Remember, we're in two-dimensional space, right? So it's everything that I can think of, but I can't have an x of 3. So it's almost like, I'm not going to say it's an asymptote because I'm not drawing a picture here, but if this is my x-axis, this is my y, if this is 3, I know that I can't plug in any points that live on that vertical line, right? No points can come from that line. Also, I need to satisfy this inequality. So this is where we go back to college algebra. And we are now going to take this right here. This is called a linear inequality. A linear inequality. And my question to you, and raise your hand if you know, how to solve a linear inequality. Because there's different ways. So if you have a method, raise your hand. I'll be happy to hear your plan. You remember how to do? Because look, it's important as Cal 3 students to understand the difference between solving a linear inequality versus a quadratic inequality versus like a polynomial inequality or a rational inequality. They all have different sorts of approaches. So how do we do it? Do you have a way?
I mean, the way that I remember doing it is that you solve for like either y or x. I guess in this term is y.
Uh-huh.
If y is greater than or equal to the function, it's obviously the line, and then above.
Then you like shade above or below.
Right.
Okay, so that's one method. I personally don't like that method only because because you have to remember which way to shade, right? Like you have to remember. So I think a way that has always made sense more to me is, and this is just, does anyone else have a different way? I mean, that is a way, it's taught that way. Does anyone have a different? It's okay, I want these responses because I wanted someone to tell me that because I know you've learned it that way. I think this approach might be better. I mean, just my opinion, all right? So what I do is I treat it like an equation first. So forget that it's an inequality at all, okay? Treat it like an equation. And then graph that, that's a line, okay? I'm gonna graph that by solving for y, right? I just move the x over, move the 1 over. That should be something we can all graph, right? Because it's a line, it has a slope of -1, it has a y-intercept of -1. Y equals mx plus b. Right, so I should be able to graph that line. And so I go to a y-intercept of -1, there's a point, and then my slope is -1 as well, so just a rough sketch like that. Okay, that's the graph of that line. Now, let me go back to the inequality. If there's a bar underneath, right? Then I'm going to include the line. The line is part of my answer. Now, as far as shading, I don't do that. What I do is I just pick a test point. I know I'm either going to be everything above this line or below. So I pick a test point, and the most natural test point is the point 0, 0, if it's available to you. If I plug 0, 0 into the original inequality, does it work or not? 0 here, 1 is 1 greater than or equal to 0. Yes. So that point satisfies the original inequality, which means everything on that side of the line is shaded. So I'm shading like this, right? Done. Now, let's combine that with this over here. So back over here, I had that x could not be 3, right? But it has to be also all the points. This is -1. Not a very good picture there. Okay,